Any questions about last class? We are going to recapitulate most of the material from last class because it was a bit abstract. Hopefully some of you definitely looked at it, but hopefully all of you looked at it and tried to get a sense of what it is. But we will start again so we can look at all the formality once again, and we will all become comfortable with the material. So what are we talking about? We are talking about interacting systems. Specifically, we are talking about classical fluids. But what do I mean by that? Let me be very explicit. Let's draw a picture here. What I mean is, let's imagine a box, okay? It could be a cubic box, it could be a non-cubic box, I don't care. It's some box. Let's say we have a box, and let's say this box has lots of atoms inside it moving around these, and I call it atoms, but if you zoom in on one of these with a microscope, it might actually be a complicated molecule of sort. Okay, so it's some atom, some molecule, and I'm just going to call it a particle. Okay, so I'm not going to care about the internal structure. And let's come up with a name for the axis. So if I call this X and if I call this Y, then as per cross product rule, I am in trouble. So let's go the other way. Let's call this one as Y, and then X cross Y is Z, which goes up. So that's my X, Y, and Z axes, okay? So the question that we are facing is, what is the probability of finding molecule number? And let's say we label these molecules, okay? Let's say we have given them names. So let's say we want to calculate the probability of finding particle number or molecule number 1 at a given location R1. And it's a coordinate system, so we can say particle number 1 at given location X1, Y1, Z1. And to be very, very clear, the box has n particles where n is way bigger than 1. The box does not have only one particle in it. The box has many, 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 many particles, and we are talking about what is the probability of finding any one particle at a time at a position x1, xyz, or x1, y1, z1. We can generalize this. We can talk about the probability of finding two particles, and we color them. So we are talking about specific particles so far. We talk about the probability of finding particle number 1 and particle number 2 at R1 and R2. This will be probability 2. And now it will have not just 3 coordinates, but it will have 6 coordinates, right? X1, Y1, Z1, X2, Y2, Z2, so on and so forth. And we could generalize it to probability of finding K specific particles at R1, R2, Rk. So this probability is called the distribution function. Now, most of the times when you have a box full of some molecules, you're not going to care about which molecule is found at R1, which molecule is found at R2. You would be more interested in the question of finding any molecule at 1 or R1 and any other molecule at R2. You will stop to care about the identity. This led us to the concept of reduced distribution function, rho. And let's just talk about 2. For 2 particles, we easily generalize it to k particles. So rho 2 of R1, R2 accounts for the fact that the first particle could have been picked up in n ways. The second particle could have been picked up in n minus 1 ways. And this multiplied. And so this probability is going to be more than just P2. Where P2 itself is calculated by integrating out everything but R1, R2, dr3, dr4, drn, e to the power minus beta u of R1, Rn. This is how we get P2. And if you multiply it by n minus 1, you get the reduced distribution function. Now, we had some discussion about why don't we divide by 2 here? Why do we multiply it by n minus 1? Why don't we multiply it by n choose 2? There is no right reason for it. We could have done it that way, but it is convenient for us to multiply by n minus 1 because as we saw last time, and Emma provided a proof for it, hopefully you all went through it, I will go through it again. For independent systems, rho 2 R1 R2 is nothing but rho square. This is for uniform isotropic fluid. Rho is equal to density of the system. So if you had that 2 dangling over here, then you would not end up with rho square, right? You would end up with rho square by 2 or something like that. So which is a bit inconvenient. That's why we did not provide a 2 over there. So, and we will go through this proof here. So, and specifically, rho 1, which is the reduced density function, reduced distribution function of finding a particle at R1, which is some location, so this is my vector R1 over here. So finding a particle at a location R1, if you have a uniform isotropic fluid, this is equal to rho, is equal to density, only in uniform isotropic fluid. If you did not have a uniform fluid, then clearly this won't be true, right? And you can see how powerful this framework could be. Instead of this, you could be looking at electrons, right? Imagine if you have S electrons, then it is uniform and isotropic. So everywhere it's constant. But if you have P electrons, you have a shape. If you have a dumbbell shape, and clearly it's not isotropic anymore. So, but for uniform isotropic fluid, rho R1 is equal to rho. This we proved last time. What we did not prove, and we left it to Emma to do it, and which she did, and she's still in class, so that's a good sign, I think. So in order to do this, we think about rho 2 of R1, R2. Let's call it Emma's proof. So in order to do this, we write down the definition. What is this? This is n minus 1, P2. And I'm also thankful to Nathan for writing the proof because it showed me something that I should have mentioned earlier, which is easy to forget, that even though we are talking about 2-particle distribution function, we are talking about 2 particles out of a very large number of particles. The box itself has n, a huge number of particles. So if this is really an independent system, if independent system and n much more than 1, very large number of particles, then rho 2 R1 R2 is approximately n squared multiplied by the probability of finding particle 1 at R1 and particle 2 at R2. Notice I have written 1 over here. I have only specified R1 and R2 differently because this 1 corresponds to 1 particle density. Okay, now it's an independent system. So these probabilities are going to be the same. So this is going to be n P1 R1 whole squared. So, or rho 2, and Emma's proof does a cleaner job of explaining this. I'm just trying to go through the ideas once again. So please look it up on Slack. It's posted over there. And that's it. That's all we needed to show, because NP1R1, as we showed in the proof for this thing last time, is rho. Therefore, rho 2 R1 R2 is equal to rho square. So this is interesting. This is telling us that if it was not a uniform isotropic fluid, if there was some directionality, if the atoms were talking to each other, then in general, rho 2 R1 R2 will not be equal to rho square. It will be different from rho squares because why will it be different from rho square? Because what it means that if you know something about a particle being at 1, it is telling you something about a particle being at 2. It's giving you some information. Imagine that all particles were interacting through some sort of spring-like interactions. That's the simplest interaction that we can think of, right? They experience each other. What the spring means is that the atoms cannot come too close, they cannot come too far. If they go too far, the spring brings it back. If they come too close, the spring says, go away, something like that. So, which means that if you have a particle here at 1, you know something about the probability of finding another particle in its vicinity. You know you won't find something too close to it because, well, there is a spring acting between them. And you know you found, and so it will have some equilibrium distance next to it. So most likely, this is not going to be just a product of the density squared. The things are not, it's not going to be just density squared because things are not independent. So in this case, we define this difference between both of them, rho R2, R1, we define as being, or the ratio of both we define as being the D, what did we call it? We call it, some books call it correlation function, some books call it decorrelation function. It's the same thing. So we are going to call this as G2 of R1, R2. Okay, so this is our decorrelation function, which quantifies non-independence. It's again a funky word to use. It's like negation of negation, but it tells you if the atoms in the system are really independent of each other or not. If G2 of R1, R2 is equal to 1, then the atoms are indeed independent. Further, so this is all quite generic. We could have even generalized it to G of K if we wished, but we simplified at this point. We said we are going to we will focus on spherically symmetric molecules with interactions. We are not saying that these molecules won't be talking to each other. They talk to each other, but they are spherically symmetric molecules, in which case G2 of R1, R2 will depend only on modulus of R1 minus R2. Okay, so what does it mean? It means that in this box, if you took this pair of atoms, 1 and 2, okay, and if you rotated it, translated it, and brought this pair over here, so that now one looks like this, and 2 looks like this. So see, I have done two things. I have translated it, I have rotated it, right? Earlier, the 1, 2 was leaning a bit towards left. Now the 1, 2 is leaning a bit towards right. But what I have done, kept constant, is the distance between them. If I keep the distance between them as constant, then it does not matter where they are. That's the idea over here in spherically symmetric molecules. This thing will not depend on where you're looking at it. If you keep rotating it, the only thing that matters is, so here I had this as R1 and this is R2, as long as R2 minus R1 is the same. So now this is new R2 and new R1. As long as R2 minus R1 is the same, this picture does not change. Okay, so that's what we are looking at now. So in this case, we can call this as R, and this thing we can call as G2 of R. And since we are mostly going to look at pairs of particles, we will just call it G of R. And that's what we are going to talk about starting today. Any questions about this? This is a recap of what we did last time.
So I just want to make a quick connection with the quantum case,
Mhm,
because here actually the rows here can be interpreted as density matrices.
mhm,
Say for the if we represent the row as density matrices, then when row row 2 over row squared is equal to 1, then that corresponds to the pure states, or otherwise there will be some mixed states. But
mhm.
um, but here the correlations or the or some decorrelation function.
Mhm.
These are purely classical, right?
Mhm. I don't know if you noticed, we were quite explicit about it, right?
Yeah. Then what does that mean physically about the decorrelation function?
I'm not going to go get into quantum at this point in this. Quantum fluids are complicated. You can generalize this framework, but it will be quite a stretch if this framework will work or not. So what you're asking is a very good question. And at the cost of disappointing you, I'm not going to get into that right now because there is already a lot to learn here, okay?
Okay, thanks. Yeah, just saw the funny connection.
No, no, there is connection. You're absolutely correct. What you're talking about, things such as this, looking at trace of rho and things like that. And I don't think it'll be trivial. I don't think it'll be trivial because already in the classical stuff, Macquarie's book has multiple chapters devoted to what we are doing. And that's why we were very clear we are looking at classical fluids. Quantum fluids are complicated. The first reason they are complicated is because our dividing by n factorial type approximation doesn't work. And things get very complicated. So let's not go there at this point, at least in this class. Okay.
Thanks.
No, I feel very bad when I quench a student's enthusiasm. I didn't want to be like that, but we have a lot to study. So let's stick with classical fluids for now. And but I'm taking notes of when you bring up these things. It might affect your final project in the exam. So it's important that you keep bringing these things up. And if possible, also send me a note on Slack when you, Jinchen or anyone else, when an idea like this comes to your head. So when I assign final papers for papers to read for either a homework or the final exam, I will give you a choice. Maybe I can find a paper like this. One thing I can mention to you, especially Jingchen, is to read a paper by Chandler and Wolinis around 1970s, maybe 1978. I'm not so sure, which is ring polymer isomorphism. Okay, you might enjoy that paper. Normally I give this paper in 687 towards the end to read. This paper is very interesting because what it does is to say that an quantum particle can be mapped reversibly into a bunch of classical particles interacting with harmonic springs. Okay, so it maps it into a bead of classical particles, and that's one way of dealing with it, but it's way beyond of where we are. So if you cannot find this paper, ask me for the reference and I will send it to you. Okay, this will give you some
Yeah,
idea.
yeah, thanks.
This
Yeah,
uses
yeah.
something called Trotter formula, and more specifically it uses Feynman's path integral formalism in order to do that. So you might enjoy this problem if you're interested in how to study classical. Notice I wrote only one particle over here. If you have two particles and they're bosons, this will still work. You will have two polymers. But if these two particles are fermions, then life is in trouble. So that's a whole open area. It gets quite advanced. But right now, let's stick with classical fluids. Okay, good. So we are talking about this is for Jing Chen et al. Optional. So if someone is looking at the notes later, don't freak out as to where did this come from. Okay, so we are thinking about this G of R, which is really G2 of R1, R2, but we are looking at spherically symmetric molecules. So it doesn't matter what is the magnitude of R1, what is the magnitude of R2, or in things like that. All that matters is the modulus of R2 minus R1. So for this, we are talking about G of R, which we call as the radial distribution function. This is something which is extremely useful because we can get it from scattering experiments, and it tells us a lot about the interaction in these systems, and that's what we are going to work on in the next few classes. First of all, let's get some intuition into what this G of R is. We are going to plot it for typical materials, typical molecules, and we are trying to develop some intuition for it. So first claim that we are going to prove now is that rho multiplied by G of R, or density multiplied by G of R, is the conditional probability density that a particle will be found at a given R at R given another particle is at the origin. And this is very important. This is the first way we can get intuition into this rho G of R. So let's represent this in a pictorial way. So let's again draw our box, and so x-axis, y-axis, z-axis. So this is telling you that, let's say I tell you there is a particle. So this box is made up of lots and lots of particles, right? Let's say someone told you there is one particle which exists at the origin. You know this information. Conditional on this information, what is the probability density that you will find another particle at a distance r from the origin? So I've tried to draw a sphere. It's hard to draw a sphere in 2D, so it looks like a circle, but it's a sphere. So this is a sphere of radius r, and my claim is that rho G of R is the conditional probability density, conditional on the knowledge that you already have one particle at the origin. So this is our first intuition into rho G of R, and all the plots that we make next are going to depend on this. So let's try to prove this. How do we do this? And I don't remember, but in the first class when we started this semester, when I asked you for your favorite mathematical equations, was there anyone who said Bayes theorem? Did any of you say Bayes theorem from probability? Maybe not. That's okay. So let's start. So we are looking at rho G of R, right? So let's write it down in the form as 1 divided by rho multiplied by rho square multiplied by G of R. I haven't done anything profound here. I have just multiplied divided by rho. Okay, that's fine. But now we can write this as 1 rho multiplied by rho square G2 of R comma 0, right? That is the meaning of G of R in a spherically symmetric molecule system. G of R means G2 of R comma 0. This in turn is equal to rho 2 of R comma 0, where the numerator divided by rho. How did we get that? Remember, rho 2 of R1 R2 is equal to rho square multiplied by so let's call this equation as equation number 1 for rho 1, and let's call this one as equation number 2 for this interdependence term. Okay, so this is using equation 2, or this can be rewritten as rho 2 of R comma 0 by rho 1 of R. This is proportional And I'm saying proportional because I have to worry about the n that comes in the numerator and denominator, but this is proportional to the probability of finding a molecule or a particle at the origin. And let's not use the two term here because that's, yeah. So this is proportional to the probability of finding a molecule at origin and a molecule at R. And the denominator is proportional to finding a molecule at position R. We are talking about isotropic fluids. So this is the same as P of 0 comma R divided by P of 0 because it doesn't matter which R you take. And if you recall Bayes' theorem, this is nothing but the conditional probability of finding a molecule at position R given that you have another molecule at position 0. So Bayes' theorem says that P of A given B is equal to P of A comma B by P of B. If you haven't really used Bayes' theorem in a while, this might appear confusing to you. Chandler talks about this proof a little bit, but please go through again. This proof is important because the plots that we are going to draw next, which are really the intuitive part of G of R, depend on this proof. If you don't understand it, it will be confusing. So first, let's again look at the statement, at the claim.
So is the R and the G of R, is that like a scalar or is
Yeah.
that a vector?
I wrote modulus here, right? So it's always going to be a scalar.
Okay, but then in the P of 0R, it's a vector?
No. It's not a vector. It's always a scalar. It's this P of 0 comma R means knowing that a particle is at probability 0, what is the probability of finding someone at a distance R in this shell?
Oh, but wasn't the row 2, didn't that have like the x1, y1, z1?
But we are always talking about isotropic systems. We have moved to isotropic land now.
Okay.
So Nathan, this is confusing because even though we have moved to isotropic systems, it doesn't mean we have gotten rid of interactions, okay? So let we are in isotropic interacting systems land, okay? So molecules are talking to each other. It's just that they are isotropic. We are not going to worry about direction. We are not going to worry about moving moving everything from point A to point B. The location of specific origin does not matter, and furthermore, rotation does not matter. They are still talking to each other, which is a fair approximation. If you are looking at things where S electrons dominate, it's a very good approximation. If you are looking at where P electrons and D electrons dominate, then it's a bad approximation. So otherwise, it's a good approximation, but interactions are there.
Okay.
So good, thanks. Good question. So we are saying, let's look at the claim once again, that knowing that a particle exists at the origin, given this knowledge, rho g of r represents the conditional probability. Given that knowledge, it represents the probability that you will find another particle somewhere on this shell. It does not tell you where on this shell, on this surface, because it's a spherically symmetric system. So everything is equal. And this is the proof. We started with rho g of r, we multiplied divided by rho, we got rho squared, then we used our equation 2 to say that rho squared multiplied by g2 is equal to rho 2, which is the reduced distribution function. And then we saw that this is like the probability, so I wrote the proportional over here, of 0 comma r, and again I can flip the molecules. If you could have also written it in this form. You could have also written it as r comma 0 divided by r. It's the same thing. It doesn't matter. We are in classical world, things can be commuted. And then this would be r comma 0. And then we will have r given 0. So let's use this claim to see how rho g of r will look. So keep in mind that rho g of r is conditional probability, I will write it down again because it's so important, of finding a particle at R given another particle is at origin. Let's say we know this. Okay. What should rho g of R look like as R tends to 0? What should it look like as R tends to infinity? Any ideas?
I'm guessing that they would the probability might, I mean, it should most likely of course die down when it reaches, I mean, when it goes to 0, because
Let's start with 0. Yeah. So what's your answer?
yeah, it should definitely like die down because can't be too close.
Yeah.
So
If I know Smrithan is sitting in a chair, I'm probably, this is where I miss a physical class. I would give this example that if you're sitting in a chair, I'm not going to go sit on top of you.
exactly. Yeah.
Remember, it's another particle. We are not talking about observing a particle there. We are talking about another particle over there. So it goes to 0. So that's absolutely correct. So with this, we can actually start talking about how g of r, not rho g of r, but how g of r will look as a function of r as it goes to infinity for any generic system. So what Smritan just said, I totally agree that it's going to go to 0 as r goes to 0. That's fair. What will happen to it as r tends to infinity? Any ideas?
It will definitely increase because as you increase the R, you tend to like find more and more particle in that radius.
Correct.
So
Correct.
it
Absolutely
will
correct.
increase.
But we are talking about it. Will it keep increasing or will it kind of become constant?
I think it will go to 1 at some point.
G of r will go to 1 or rho g of r will go to 1?
Rho g of r will go to rho.
Rho g of r should go to
So
Rho g of
Because
r
eventually it
goes
will-
to rho.
Yeah, because
You
eventually
remember
you will
density.
yeah,
Okay.
yeah.
This is a subtle point. And every time there is one student in the class who will be very upset about this. No, it's a probability, it should go to 1. But the point I'm trying to make here is that if you had a very low density system, then it should still go to 0, right? If the density is very, very low, then the conditional probability of finding something at R should be very small.
oh yeah.
So it's a high density system, it should go to rho. So this is super important. And that's why I said that claim was so important, because we could not have gotten to this without that claim. So what does this tell about g of r? G of r goes to 1, right? Because rho g of r goes to rho, therefore g of r goes to 1 as you go to very, very large values of r. And in
could
between,
you could you explain why it goes to, I mean, rho gr goes to rho as r tends to infinity?
because if you expect it to be proportional to density.
Aha. Okay.
Right? If you had no density, if you had very weak density in the system, very, very small density, then you expect that the conditional probability of finding another particle at a given distance should be very small, right? If I double the density of the system, you expect this probability to double, right?
Right, sure.
And remember, we are talking about low density systems to begin with. So don't worry about what happens in a very densely packed fluid. We are not going into that regime. So it's okay to do these things because rho is a small number. It's really a small number. So g of r goes to 1 as r tends to infinity, and all the magic happens in between. In between, what can we say about, now we have to think about whether it's a solid, a liquid, or a gas. Let's say we have a solid, a crystal, and we had a certain particle over here. So you will expect that if a particle is already at the origin, I am not going to find any other particle closer than the first neighbor distance, right? There will be some thermal fluctuations, but you're not going to find a particle closer than the first neighbor distance. So this thing will have a delta function type shape at the first neighbor distance. And let's be careful. So it will have a delta function type shape, and then it again goes down to 0, not to 1, but to 0, because it's a crystal, right? We know you're not going to find another atom in between the first neighbor and the second neighbor. Then the second neighbor, it again goes to 1 and then drops to 0. Third neighbor, it goes to again some other value and drops to 0. And I guess this infinity is really far, and it will keep doing these things depending on what you have. And at some point, it will start to go to 1. So that's what happens for a solid. Can we say anything about the heights of these peaks? So this is my first neighbor. This is my second neighbor. This is my third neighbor, so on and so forth. And we are talking about a solid so far. Does anyone have an idea? Can we say anything about the heights of the peaks?
Will the heights of the peaks depend on like the crystal structure?
Exactly correct. So Eric nailed it. It depends on the crystal structure. In fact, shouldn't you be able to tell the crystal structure by looking at how the heights of the peak are relative to each other?
Yeah. I mean,
So you can see why it's important, Eric. Can you
Oh, yeah.
now?
yeah.
So this height depends on crystal structure. And in fact, in many materials, you can have non-trivial peaks going on. Maybe you will have the highest peak at sixth neighbor. It can be quite complicated. So that's how it looks for a solid. And you will always have some scatter. In a perfect solid at 0 or close to 0 temperature, it becomes a delta function. Typically, by looking at the width, you can talk about defects, thermal fluctuations, and all sorts of things, but you have a delta function type behavior like this. Let's now talk about liquids and gases, and I will do them in another plot over here, both of them at the same time. So we are talking about G of R, R. So for a liquid is almost like a solid with lots of noise, and there is the crystal structure has been destroyed. So you get kind of similar shape. Again, what Smrithan said, at 0, it goes to 0. You can't have an atom if you know something's there. It peaks, but it doesn't quite drop down to 0. It goes down and it goes up and it goes this and that, and then it goes to 1. This is how it will look for a liquid. A liquid, if you study it, does tend to have some preferred distances between atoms, but typically it decays. The G of R in liquid decays something like this. In gas, it tends to rise even weaker at the first peak and then decays even quicker. So these are approximate plots, how you would expect it to be looking for liquid and for gas. The key point is at R tends to infinity, G of R always goes to 1. For any material, liquid, solid, gas. Before Jing Chen reminds me, no claims about quantum systems. Things can be very funny. But in extremely long correlated systems and things like that, I don't know what's going to happen. But yeah, that's why we are talking about classical systems. If you have entanglement, then I don't know how this will look like. Okay.
I have one question. So when you said that the height depends on the crystal structure, could you comment on how it depends? Like how does it, so for example, what corresponds to like a higher peak and what corresponds to a lower peak?
Well, I don't remember top of my head, but it will be like a face-centered cubic or a body-centered cubic. It's the ordering. It's the ordering of the crystal. You can go and look up plots for it's easy to calculate this actually, given the crystal structure. But every crystal structure has its own signature height of peaks.
Okay.
So simple cubic will be something. It's not trivial. It's easy to calculate, but not trivial. So it's hard enough that I can't just do it here.
Okay. Oh, no, no, I was just wondering, for example, let's say that I have a fixed neighbor. I mean, in the sense that I have a neighbor fixed at some R naught, like let's say the first neighbor at that distance. I'm not varying the distance, but I'm just talking about like what the height there would correspond to.
Yes, height corresponds to,
It would be the number of first neighbors.
Exactly how
right?
many neighbors at that distance,
Yeah.
right?
yeah,
Yeah.
which changes crystal structure to crystal structure,
Yeah,
right? That's
I
the
see.
point.
Okay.
Yeah.
Cubic, face-centered, body-centered, decorations of the lattice. It is a whole jungle out there.
Okay. So
And-
proportional to sort of like the number of neighbors at that particular distance, right?
Yeah.
Okay.
So-
Okay.
So you remind me, actually, I had a trip down memory lane. This was in 2007 for my undergraduate final exam. The professor asked me the same question, similar thing. What is the ratio of the heights for face-centered cubic, body-centered cubic, or something like that? And I told him, I don't remember. I'm never going to remember, but I can derive it for you if you wish. And the professor got very angry. He expected me to remember. I still don't remember. But good. But I will give you a paper where something like this is calculated. So these type of questions, the ones you're asking, are very important because they give me a sense of the application papers that I will give you sooner or later. Okay, go ahead.
One more question related to that. Do you have to identify the crystal based on the ratios that does the absolute like value of the first peak matter, or is it only the ratio between
think
the
it's
peak of the
mostly the
first and second
ratio.
neighbor?
It's mostly the ratio, but now if we are gonna get technical here, Eric, for crystal structure, have you done any diffraction, by the way?
Something to, a lot of my crystal stuff is because I took a materials class back in undergrad.
Okay.
So we had to
do
like
you know
worry
Bragg's
about
law?
all this.
You know Bragg's law?
Trying to remember if I do.
N sine theta is equal to 2
There is
n
the like standard diffraction law, right?
standard diffraction. So diffraction typically helps you, but mostly it's the ratio of the heights, not the absolute value.
Okay.
Yeah. And it's also the location. What value of R are they happening at, right? Because you know that's going to be even more important. You know, for a simple cubic structure, the first neighbor will happen at A, then the second neighbor should happen at, I don't know, square root of 2 times A, right? So it's the height and also the relative value of the location of the peak that tells you something. Because for a simple cubic, it's going to be, so if this is A and this is A, then you can complete the triangle and this is going to be square root 2A. But if you have a face-centered cubic structure, then the next neighbor is not, it's somewhere in the middle of the face, and the peak should happen at a smaller location. So you look at all this and conclude. Why is all this important? This conditional probability of finding a particle, this G of R, can be directly measured in scattering, in all sorts of scattering experiments, X-ray scattering, neutron scattering. The observable is G of R. With one more clarification. So G of R is useful and important, which is kind of the same thing, and tractable. What do I mean by tractable? By tractable, I mean it can be measured through scattering experiments. So those of you who are going to work with John Furcus, for example, in chemistry, will be measuring things like this, can be measured through scattering experiments. And one caveat here is that often instead of directly measuring G of R, you measure something called S of K. This is the Fourier transform of G of R. So this thing is called radial distribution function, while this S of K is called structure factor. And if you have done solid state physics or structure of materials or things like that, then you can also use Bragg's law to talk about how this will arise and things like that. you're using scattering, right? And Bragg's law gives you a formula for scattering through X-rays, for example, what should be the structure factor. So this is Fourier, and this is inverse Fourier, and they contain the same information. You can measure depending on your technique. You measure for those doing computer simulations, it's easier to measure G of R. For those doing experiments, for a variety of reasons, typically you get S of K out of the experiments. And I'm sure Nathan will appreciate this, and many others will also appreciate this business of Fourier and inverse Fourier is actually, it sounds abstract, but it's something that happens in nature quite frequently. For example, as you are listening to my voice, most likely your ear is computing a Fourier transform of what you're hearing, and your brain is then inverting this Fourier transform to actually convert it into some other information. So this going from real space to reciprocal space business is not just a mathematician's creation. It's really fundamental to how our bodies process information. And there is a reason for why they do this, is because sometimes it's better to look at certain properties, at certain physics in inverse space. In fact, John Weeks, who taught you 684, one of his most important contributions to science was that S of K, even though G of R and S of K capture the same information, it's much better if you look at S of K for most liquids. It's easier to recover information. So we are not going to talk about all that here, but the point is that these radial distribution functions or their Fourier transforms equivalently can be measured through experiments. So they are tractable. I have not shown you yet as to how exactly are they useful and important, right? So I have told you can measure them, but I have not told you why they are useful. They are useful for a variety of reasons. Why is G of R useful? So the number one reason they are useful is because if you have synthesized some new material, some new chemical, and you do a scattering experiment on it, and you get all these conditional probabilities, you are studying what is the probability that an atom is going to be located at a certain distance away, knowing that there is another atom over here. You can use this to recover the full interaction potential that the system experiences. And that's super important. You can talk about the potential energy through which atoms talk to each other. If you have this potential energy, then you can write down an ensemble. You can pick an ensemble and write down a partition function of your choice using this potential energy, right? Let's say canonical ensemble is just going to be summing over e to the power minus beta u, and you can get all sorts of thermodynamic properties. So G of R contains all, and that's a bold claim, it contains all thermodynamic information. It's complete. If you measure G of R, you can calculate free energies, entropies, whatever you want. That's why it's so important. And I will show you how to do this. What we will do is to talk about two things next. One is we are going to talk about something called, actually, I'm not going to number the more things I'm going to talk about because it might be two, it might be three, it depends on how we proceed. There's a lot we can do. Just to give you a sense, one of the things we can do is to calculate equation of state given G of R. So some of you, well, hopefully all of you recall that the simplest equation of state for a material with no interactions is PV is equal to nRT, right? But, so this is when you have no interactions. But this is not really true. One of the important equations of states that you have studied in the past is van der Waals equation of state, where you say that, okay, P is equal to density times RT. This is still ideal. And then you say how to write it in a clean manner. Then you say that, okay, well, yeah, we don't need to go to that. We say that, okay, the one way of writing van der Waals equation of state is to say that atoms have a finite volume. So we put in V minus NB is equal to nRT. So that gives us P is equal to nRT by V minus NB. And then we say we have a second correction term, which looks something like A n square by V square, right? This was our van der Waals equation of state that you have probably studied. Well, I'm pretty sure you have studied in your PChem. And we will show how these A term and B term are natural consequences of G of R. You can actually calculate this A and B term out of G of R. This is ideal gas equation of state with no interactions. This is van der Waals equation of state for an interacting system. There are further equation of states. Let me number the page. There are further equation of states which look like this. Pressure divided by kT is equal to rho plus some term B2 depends on temperature multiplied by rho square plus some term B3 multiplied by temperature depends on rho cube, dot, dot, dot. These are called virial equation of states, which also correct for the interaction between different particles in the system. And these terms B2, B3 and all can be calculated from G of R. So it contains a wealth of information and we are going to work through all of this. Okay, so, but the first information, so G of R, we will see how G of R can give equations of state. And equations of state are possibly one of the most important things in chemistry. If you are studying some complicated molecule in some outer solar system, you have sent a satellite out there or somewhere very, very far, and the, like the rover, which is on Mars currently, is carrying out scattering experiments. That rover is sending us back G of R values. That's apart from many other things. One of the things it's sending us back is G of R. And people, and this is no exaggeration, because when I was in grad school, one of the friends I used to go rock climbing with was actually the chief driver of one of these, something called the Curiosity rover. But so I knew friends who were actually working on this, and they would get G of R back from it, and then they would invert this G of R to recover all sorts of information about what is happening on Mars. So if you follow through the formalism that I'm developing in the next few classes, you will see how this can be very useful. I'm not telling you how to calculate G of R. That I'm leaving on either an experiment or a computer simulation. I gave you a sense of how it might look like. For a liquid, it looks like this. For a gas, it decays quicker. For a solid, it has sharper peaks. But statistical mechanics is not going to tell you what is G of R. That has to be measured through some other way. Statistical mechanics can tell you G of R if you knew the interaction, right? If you knew this capital U of R1, R2, Rn, then you can calculate G of R. But you cannot, you have to know one of them. If what we're doing now is to connect both of them. So if you knew G of R, you can calculate U. If you knew U, you can calculate G. But you have to know one of them. U of R1, R2, Rn, the interaction between molecules is not so amenable to direct calculations. You cannot just calculate it directly. So in computer simulations, U of R1, R2, Rn is known. Does anyone know what is it called typically in computer simulations? There is a term used for it. Any ideas? Nathan, you should know.
Like Leonard Jones and electrostatic.
Sure, but what's the generic name for it? It starts with a F.
Force field.
Yeah, there you go. So force field is known in a computer simulation. So in computer simulation, typically the process is to take a certain force field, simulate the system with it, solve Newton's law of motion, and then calculate my G of R. In experiments, U of R1, Rn is not known. So people start with the G of R that they measured, and they calculate U of R1, R2, Rn. And people like Jeff Klauda and chemical engineering try to do both of these things in an iterative manner so they can come up with good force fields that describe a given material or a molecule or anything like that. Okay, so we are going to study all this. Our first use of G of R is related to something called potential of mean force. This is the first application of G of R that we will show, that how G of R can tell us something quite important about a system. So I'm going to work through this proof. And again, I will repeat from here next class, because this is all a new level of abstraction. We have to proceed slowly, otherwise we won't understand many things. So the claim I'm going to make is that, let's draw a picture first to understand this before we get into all of the math. Again, let's imagine our box again. And let's say in this box, I have lots and lots of molecules. But I have two special molecules, okay? So you could imagine, for example, that the black particles that I drew over here are a water molecule. Are lots of waters, and these are two specific water molecules that I'm going to focus my attention on, okay? And what I'm going to do is to fix these two at some location, R1 and R2. I have been drawing my origin on the top left, so let's draw from there. So this is R1 and this is R2. I fix them, okay? So N total molecules, fix two of them at R1 and R2. Then I ask you the question, given the full interaction energy of the system, if I want to calculate the force that molecule 1 experiences due to molecule 2, how will I write down that force? So this will be minus du of the full n particle potential energy divided by dr1, right? So this is the force the molecule 1, this is the force experienced by molecule 1. But on top of this, I have to have a minus sign, right? Because force is equal to minus of potential. So I have a very complicated n-body potential, and I differentiate it with respect to R1, right? This is the force experienced by particle R1. Now, what I do is to average this force. So I use my bracket notation, keeping R1 and R2 fixed and varying everything else. So this looks very abstract, but let's take a moment to get an intuition for this, what this is. My claim is that this is actually quite important. So I'm letting all these other molecules that I'm coloring in pink right now move around in all possible ways that they can move around, okay? And once I do that, I calculate the force relative to between these two after averaging over everything else. So this is so let's write it down in words. Hopefully that will make it a bit clearer. So two molecules held at a fixed distance R12 apart, and we are talking about isotropic systems. So instead of R1 and R2 separately, we just switch to talking about R12, which is a scalar. R12 apart, when remaining n-2 molecules are averaged over all possible configurations. Now, the different configurations will have their own different weights, right? If we are in a canonical ensemble, we know that every configuration will be having a weight which is proportional to e to the power minus beta u. Because if you have a very, very high potential energy, the weight for that configuration is going to be very small. In other words, if you take all these little pink molecules and stuff them in a ball very close to these two, then that's not a very likely configuration. The contribution of such a configuration to this average should be very small, right? So we take these two molecules, fix them at a distance R12, and allow everything else to take all possible configurations they can, but every configuration has its own weight, which is the Boltzmann weight. So this is e to the power minus beta u. Then minus d by dr1 u of rn is the force experienced by particle 1 when Rn is equal to R1, R2, Rn, right? For all given values of the particular R. And average of this thing minus d by dr1 u of Rn is the mean force experienced by particle 1, mean in what sense? Averaging over R3, R4, Rn, all of them. Similarly, you can write down minus d by dr2. That will be the mean force experienced by particle number 2. And what we are going to show in next class is that this thing, this mean force, and this is where I'm going to stop because this is already quite abstract and we have to again take a step back next time and work through it again. I really, really request you to go back and read Chandler's chapter number 7 on classical fluids so we can stay together in understanding this. It will really help you understand what I say a bit better. I mean, yeah. So what we will show next time is that this average value of d by dr1 u of Rn is given by kT multiplied by d by dr1 of log of g r1 r2. In other words, if you're really thinking about a spherically symmetric system where there is no point in talking about R1 and R2 separately and you're just talking about d by dr of u Rn, then this thing is given by kT d by dr of ln g of r. So the force comes, you could have obtained the force by differentiating the full n particle potential energy, which is not known, or you could have obtained the force by differentiating this distribution function, this radial distribution function, g of r. And another thing to notice is this is averaging over all n-2 particle, but on the right side, there is no extra averaging because G of R has already done it for us. So if you can calculate G of R, take its log and differentiate it with respect to R, you learn something about the potential energy. You are directly saying what is the gradient of the potential energy, and then you can back calculate it to talk about the potential energy. So differentiating G of R gives us the averaged force. In physics, whenever something can be differentiated to get a force, what is the name that we use for such a thing? Maybe I said it too convoluted way. And think about, or maybe I did not. Does anyone see what I mean?
Newton's law.
That's correct. But so what I'm saying is differentiate something and put a minus sign to get a force. What is the typical name for this thing in the bracket?
Potential.
Potential.
Yeah, there you go. It's potential, right? Potential energy or something. But when we differentiate a potential, we get a force. And here, this is the averaged force. And we are getting it by differentiating log of G of R. So log of G of R is like a potential. This is why G of R, and you could have called log of G of R, but in general, G of R is called potential of mean force, abbreviated as PMF. This is of super importance in condensed matter physics, in chemical physics and things like that. What is the potential of mean force? Because if you have G of R, you can calculate its log, differentiate it with respect to R, and you are talking about what is the mean force experience between two atoms averaging over everything else. So this is what we are going to prove next time. We will work through it, then we will come back to the statement, so you will get a chance to look at it again and again until this becomes intuitive to you. Okay, any questions? So before I forget, just to remind, I made it clear in last class that the midterm, which will be released next week as per the instructions on the website, will include all material before and on 325. So the topics that were taught on 25th March are a part of the midterm. Anything after 25th March is not a part of the midterm. I will not be asking you about G of R on the midterm. It will take time to go through this. We will have a homework after the exam. We will work through G of R. Okay, any questions? This is all abstract. Please go and read Chandler's chapter 7. It will help you understand. It's worth your effort. You will like this stuff. It's really nice. It's useful. And it is a way of having fun, I guess. It's really, and it's important too. It's not just fun, but it's also important. So if no questions, see you later.